Okay, welcome to the IMA Northwest Branches Student Teacher Talk using Origami in the mathematics classroom. This is our branch's first online talk, so please bear with us with the technology that's new for us as a branch. Our speaker, Sue Pope, has vast experience in maths education, including as a teacher, a local authority advisor, a teacher educator in higher education, and working with qualifications authorities. She's also been involved with maths associations, including the IMA and the ATM. Her session today is a practical session, so you'll need some paper in squares and rectangles at the ready. Please do join in with the activities, as it will help to make the session and the activities more memorable. The session is being recorded, so if you get left a little bit behind, don't worry, you will be able to revisit it when it's on the IMA's website. If you've got any questions, can you pop them in the Q&A section rather than the chat, as this is where we'll be monitoring questions. And then at the end of the talk, we'll have time to ask Sue the questions. So without further ado, I'll hand over to Sue for today's talk.
Okay, thank you very much, Rachel, and good afternoon, everybody. This is my very first virtual talk, so I hope that I managed to communicate effectively. I want to start by flagging up the wonderful Learning Mathematics with Origami book that's available from the Association of Teachers of Mathematics. I did not write it myself. I wrote it with my wonderful partner, Ken Lam, and I want to just acknowledge his tremendous contribution to all my work on using origami in the mathematics classroom. And I really commend this booklet to you. It's there's free student membership of the Association of Teachers of Mathematics. So if you're a beginning teacher, welcome. You're embarking on the most tremendous year of your life. Becoming a teacher is a life-changing experience for definite. But the Association of Teachers of Mathematics has been my professional home throughout my career and provides a wealth of wonderful resources to support you in the classroom, and including this. And as a student member, you get discounts on all of ATM's publications. So I hope you'll make the investment and enjoy using this booklet and all the wonderful ideas that are in it. And I'm just going to talk about a small number of them and hopefully share with you some of the reasons why you might want to use paper folding in your classroom to explore mathematics. You know, paper is a very cheap and versatile resource. Schools, in my experience, are often full of recycled paper. So, you know, paper that was good for one thing and is no longer good for that original purpose. Certainly when I was teaching, I used to have a box of paper for recycling in the classroom, which we regularly used for folding activities. The paper I'm using today will generally be clean, fresh paper, but that's because it's quite some time since I was a teacher, and now most of my teaching is with things like masterclasses or workshops for teachers or members of the public and so on. So maybe it's a damage limitation thing. You'll be able to decide for yourself. But one of the reasons why I enjoy using paper and so on, not only is it interactive, but also it gives you an opportunity to really develop your mathematical language. And those of you who are beginning teachers, I know you're very early in your careers, but one of the things that's really important in all learning, but I think particularly in mathematics, is the use of language and being clear. So what I'm showing you here, hopefully you can see them okay, are two rectangles, but one of them is a regular rectangle in that, as well as having all the angles the same, all the lengths the same, and of course we call that a square. But if I want a word that distinguishes these two, then I need to use oblong for this one, because it has one orientation longer than the other. But they are both rectangles because, as the word suggests, they've got right angles in the corner. And if you try making shapes with just right angles in the corners, then actually these are the only shapes you can make. And that's one of the wonderful things about mathematics, you know, that generality. You know, these things are always the same because. So to start off with, I'd like to invite you to take a square of paper, and to help me with my talk today, what I've done is I've actually pre-folded things to make it that bit easier, and it's actually a strategy that works quite well in the classroom. So we're going to take our piece of paper and we're going to fold it into a 4x4 grid. And I just want to make absolutely clear that when you make your folds, if you don't need to, it's always worth unfolding them. So I've put in that halfway line for my square, and now I'm going to fold down to that center line and up to that center line. Don't do it in midair the way I'm doing it. I'm doing it to show you. It's much easier if you do it on the table, because the table will help you to get nice sharp creases. Okay, so I've now got 3 folds, and I'm just going to reinforce those with a pen, so hopefully you can see them. Okay, it's really very strange for me not to be able to see what you're doing. Ordinarily this would be a practical session and I'd be able to walk round and have a look what you were doing and interfere if you seem to be having any problems, and I'm really sorry that I can't be with you to do that. Okay, so we've got those 3 folds in, hopefully, and then we're going to turn the paper and repeat. So yeah, again, halfway, open it up and do the other 2. Okay, so now we've got our 4x4 grid, and I'll put in those folds that I've just made. And when you're in the classroom, reinforcing your folds with a dark pen can be very helpful, especially as often those learners with who are most challenged with their eyesight will often sit at the back and then tell you they can't actually see what you're doing. So you might find it helpful. The other thing, of course, is if you're in the classroom, you can walk around with your demonstration and people can have a good look. I hope this is working for you. But now you've got your square with that's actually been divided into 16 pieces. You can now use it to say things like, show me a half, yeah, or show me a quarter, or show me 3/8. So I might do it that way, but I could have started off by folding 3/4 and then folding a half, and that helps to reinforce relationships and equivalences, which are such big ideas in mathematics. Obviously, the other thing that this does, you've got 16 little squares, so you've got equivalents built in here. Yeah, so 16/16 is a whole, 4/4 is a whole, you know, 8/8 is a whole, etc. And all of those relationships, which are so important for young people to understand. At the start of secondary school now, children will have met fractions in the primary school and will have done arithmetic with them, but the chances are their conceptual understanding of fractions will be quite weak. Using a rectangle is always much more powerful than using a circle. There's plenty of research that cutting up pies is one of the worst things you can do if you want to help children to learn about fractions. Using rectangles or strips is actually much more powerful. So the other thing you can do with this square is say, not that it's 1, but actually it represents 4 or 256 or some other thing, and use it again to illustrate proportions of that. The other thing to do with fractions is to use strips. So if you have a strip of paper, yeah, you can fold it in half. You can fold it as we did for the square, into quarters. You can fold it into eighths as well. But the thing about folding the strip is you can then mark it up to show an eighth, a quarter, 3/8, a half, etc. And this helps to reinforce the fact that fractions are quantities. They are numbers on number lines. And if we want to do arithmetic with fractions, it's actually quite important that people go from the bits of a whole to actually part of a number line, which obviously then extends. And with any model, one of the things you always want to think about is what happens when we fall off the end. So, you know, here's number 1, what comes next? Yeah, and you can always say it's 1 1/8, or you can say 9 1/8, and so on. I always loved counting in my classes, and counting in fractions is great because the thing about fractions is they're nothing like ordinary numbers. And so, you know, I can say 1/8, 2/8, 3/8, 4/8, 5/8, and actually that's really easy. But once I start saying 1/8, 1/4, 3/8, half, 5/8, 3/4, that starts to get quite messy, and it's even worse once you get into 16ths and so on. But that notion of equivalence really important for learners. So there's just a couple of things to share with fractions, and I guess what I'm hoping to do in today's talk is to show how some, you know, a very wide range of ideas to do with mathematics can be addressed using some paper folding. Now, I suggested for this talk you brought along some A paper. Okay, now this is really very special paper because when you halve it, yeah, you end up with an identical shape, yeah, A5 obviously. And I always enjoy working with young people and you know, saying, well, if I take, you know, 2 pieces of A5, that's A4, and if I take 2 A4s, that's A3, and then, you know, 2 A3s will be A2, and so on and so on, and we get to A1, A0, A-1, because why not? You know, this is mathematics, we can just continue the pattern. And the important thing with similarity, of course, is that if I put in the diagonal, it would go through both of them. But because of this property, it's very easy to derive the proportions of the paper. Now, I'm not suggesting you get your ruler out and measure, but if you say the shorter length is 1 and the long length is X, thread, whatever you like, then when I halve it, the longest length is 1 and the shorter length is exactly half of X, say. So using similarity and the proportions, that means that, yeah, the ratio 1 to X must be exactly the same as the ratio half X to 1. So if you write down that equality, what you get, and I'll write that down, yeah, so I get X is the same as 1 divided by a half X. So if I multiply both sides there by a half X, I hope you're managing to see this. So I've got X, half X squared is 1, which means, of course, that X squared must be 2. So the proportion of my paper is 1 to root 2. And that's a very special relationship because I'm sure you know that in a unit square, the length of the diagonal is root 2. Okay, and we can illustrate that with our rectangle and square. Okay, I hope that's kind of making sense. But, you know, that's a very accessible proof, I would suggest, to, you know, probably learners in year 9. and maybe slightly younger, obviously, depending on their capabilities and experience. Now, when you have a rectangle, I'm sure you've all had to make a square from a rectangle, and you know that the way that you do that is essentially to fold in, sorry, I'm just looking for yet another piece of paper, but you basically fold in the diagonal of the square. Yeah. And if you fold in both diagonals, as I've done on here, I'm just going to show you. Fold in both diagonals, you end up with a piece that I've already removed, if I can find it. Beg your pardon. Yep. This small piece of paper, okay, which is sometimes called the leftover rectangle. And if you've got to take a piece of paper and you've done that so that you've made yourself a square, and you want to tear off the leftover rectangle, the thing to do with that is to just make sure you fold the paper several times. That weakens the paper and makes it easier to tear that strip off. Okay, now this leftover rectangle, and I have one that I prepared earlier in a slightly different colour. If you fold in the two mirror lines for that leftover rectangle, and I've done it in a different colour just to make it clear what I'm doing. Okay, and you line it up with the diagonals of your square, like so. Okay, you can then turn in the small triangles. Remarkably, it exactly fits. In other words, yes, that length, which is actually root 2 minus 1, yeah, is exactly the diagonal of the square. Well, that is the length of the triangle you're folding over. And if you rotate it 180 degrees, sorry, rotate it 90 degrees even, that would be good, and line it up again, you can fold in the corners. And actually what you've folded is a regular octagon. Okay, so if you are wanting to work on shapes with learners, then folding them from paper will give you very accurate polygons to work with, but also that nice physical activity that really helps to reinforce what's going on. Okay, and with any shapes that you fold, you can ask things like what size are the angles, what are the lengths, what are the area, you know, how does it compare with the unit square you started with, if you want to call it a unit square. Obviously the lengths are arbitrary really. Okay, so the next thing I'd like to go on to, because you might think, well, that's fine, I can do a square and I can do an octagon. What about a triangle? Well, those of you who know your geometry well may know that one of the things you cannot do, excuse me, I've got all these bits of paper that I'm trying to work with, so you must excuse me. Right, this will do. But one of the things that you can't do with a pair of compasses and straight edge is a trisection. But actually, in paper folding, you can. So I'd like you to take a piece of A paper and fold it in half longwise, okay? And when you've done that, open it up. I apologise, my paper's all pre-creased. I warned you about that, but I'll just reinforce the crease I've just put in. Okay, I've just done that. And now this is always the most difficult fold I find to explain. What you're going to do is make a fold with two fixed points. One is a corner and the other is the fold you just made. So you're going to take that corner and you're going to put it up on the fold you just made, but so the fold goes directly through the corner. Okay, so what you've ended up with is a trapezium. All right. Now, this is not just any old trapezium. This is a really special trapezium because, and you can probably deduce for yourself, these are two right angles. So these two angles must add up to 180 degrees. Yeah, the obtuse angle and the acute angle. And it's quite a nice little exercise to figure out exactly what magnitude those angles are. If you ask learners what they think, they'll often tell you things like, oh, it must be 45 degrees, even though you didn't fold this down to that edge, when it would be. But if I just show you how you can put, beg your pardon, how you can put two together. Yeah, this illustrates what I just said, that the obtuse angle and the acute angle together make 180 degrees. But the other thing that you might find you can do is to, if you've got two of them, is to put the acute angle up by the obtuse angle, and you'll see that actually it's that two of these acute angles is the obtuse angle. In other words, what you've done is the acute angle is 60 and that's 120. I would normally give young people quite a lot of time to discuss the properties of the shape that they've made and to figure out the angle size, you know, with their peers. But obviously this is a talk, so I'm not going to do that. But what I would say is that now, because we've got 160-degree angle and we've got a 120-degree angle, there's an equilateral triangle here just dying to come out. So what we're going to do is to help it come out, and we'll do that by bisecting the obtuse angle, by bisecting that 120-degree angle. And again, when you're working in a classroom, this is something young people find extremely difficult. They don't appreciate that an angle happens at a point, and that means if you're going to bisect the angle, you're going to have to take these two edges and join them together. Okay. And we're still not quite at an equilateral triangle. We've got two 60-degree angles now, but that's it. And if we count the number of sides, what we find here is we've got a pentagon. Yeah, there's 5 sides, but we've got a reflex angle. So this is a concave pentagon. It's a perfectly good pentagon, but many learners think that pentagons must always be, well, and all polygons must be convex, i.e. all the angles stick out. And obviously that's not the case. So all you need to do to finish off your equilateral triangle is just turn away this little fluffy bit, and there we go, we've got an equilateral triangle. Okay. Now, just to give us a little break from the paper, I'd like us to do a thought, I'd like you to do a thought experiment. Okay, I'd like you to imagine a triangle. Okay, it doesn't be any shape you like, and it certainly doesn't have to be an equilateral triangle like the one that we were just talking about. Okay, and I'd like you to select one of the edges of your triangle to be the base. Okay, and I'd like you to think that the vertex opposite the base is the apex of the triangle, okay, the top point. And I would like you to make a fold that is parallel to the base, okay? So you've got your base of your triangle and you are making a fold that is parallel to the base. And I'd just like you to, as you bring down that apex, I'd just like you to focus on what's happening. So you fold down the apex, what you'll find is you've made a crease and you've got a triangle. That triangle may well overlap beyond the base, but that triangle's got exactly the same angles as the original triangle. So it's a similar triangle. And there's two little triangles from the original. If you leave that apex folded down, there's two smaller triangles, and there's some overlapping bit, and there's possibly a little triangle, as I say, just hanging over the base. What I'd now like you to do is to move that fold so it's a parallel fold, but try putting it in different positions. See what happens if you just fold quite close to the apex. What happens if you fold very close to the base? Think about what stays the same and what changes as you do those things. Okay, so I hope you're with me. I hope you're managing to imagine what's going on there. One of my favourite bits of a previous version of the national curriculum was children should be taught to visualise, and I think this kind of exercise is really, really good for that. So I want you to unfold your triangle, yeah, so it's flat, and making a fold that's parallel to the base. Is it possible to just get the apex onto the base? So this time you're being really very accurate. You want to get the apex absolutely on to the base. So there's no overlap and there's no gap. And what you've got is a shape that's got one pair of parallel sides. So if I was in the classroom, I'd be asking learners, what's the shape you've made? You know, what do you notice? Why is it? And so on. So hopefully they'd tell me it's a trapezium. And they might also say that the triangle that's overlapping, there's an identical bit underneath. And that actually on either side, there's two isosceles triangles. They're not necessarily the same, depending on the triangle you started with, but they are isosceles. And I'd want them to be explaining to me why they're isosceles, how they know that. So now in your thought experiment, what I'd like you to do is to fold the two isosceles triangles, one at a time, in half. So what you'll find when you do that is that all three angles of the triangle are meeting together on the base of the triangle. And what you have actually proved is that the angle sum of a triangle is 180 degrees. You have not done any measuring with a protractor. You have not been tearing off corners, which is quite a popular approach to the angle sum of a triangle. And of course, it doesn't matter which triangle you started with, it will always be the case. So whether you had an equilateral triangle like the one we just folded, yeah, that would do what we just said. Yep. Okay, angle sum of a triangle 180 degrees, or whether you had something that was scalene and had no particularly strong properties or indicative property. Yeah, there we go. It's gone, the apex has gone down to the base to make the trapezium, and I've halved my two isosceles triangles, and I have demonstrated that the angle sum of the triangle is 180 degrees. But I've also told you something very special about the area of the triangle, because this rectangle that I've ended up with, its area is exactly half of the triangle. Yeah, the base is exactly half the original base. The height is exactly half the perpendicular height. So the area of the rectangle is a quarter of the base multiplied by the height, or if you want to imagine the smallest rectangle that could possibly contain your triangle. Yeah. So you've actually also demonstrated that the area of your triangle is half the base area multiplied by the height, and that is just, for me, this sort of exemplifies what Jeff Fulks always talks about, saying you can get a lot for a little in mathematics. So here we are with a simple fold that gives us two very powerful and important results in mathematics that learners often have to learn without really understanding why or knowing where it comes from. And you know, one of the great things about mathematics is it can all make sense, and it is all connected, and there is no need for rules or, you know, rigmaroles that don't make sense, because mathematics can make sense. So the chances are, if you're teaching year 7, maybe year 8, you will be doing these, you know, the angle sum of a triangle and area of a triangle. So I hope you'll use a piece of paper to help with that. So we're going to go back to our equilateral triangle, and one of the things I like to invite learners to do is to find the centre. Find the centre of you know, of the triangle. And after a bit of experimenting, you know, learners will often say, oh, actually, if I just fold in the lines of symmetry, it'll meet at the centre. So you might like to have a go at that. The nice thing about your folded paper is that, and if you do that, if you open it up, you will find that actually the centre coincides with a point on this half equilateral triangle that's inside your equilateral triangle. And you could find that, so I don't know if everyone can see. So I've opened it up, and there's this bit which is actually half the equilateral triangle, and you can just fold to turn that half equilateral triangle into an isosceles obtuse angled triangle. You can see, hopefully you can see that. As I say, this is my first time of doing a remote talk on origami, so I do apologise if I'm not quite making sense. But actually, the apex of that obtuse angled isosceles triangle is the centre. So rather than having to put creases, you can actually, as I say, just fold that triangle down. And as I say, normally I would invite learners to try and figure out where the center of the triangle was, and they'll put loads of creases in, and then I'll say, oh, well, I didn't need to do that. And of course, they open up their mirror lines and realize that they've all met at that point. And there's some good opportunities for geometrical reasoning on why that happens. Okay, now in the folds that you made to make your isosceles triangle, you will see that you've still got the original mirror line, the original first fold that you put in. And if you fold along that, you will find that, yeah, one of the vertices of the triangle goes down to the base. And if you unfold and do that again, and then there's one left which you can easily do, then what you have here is a great illustration of the properties of similar shapes, that if you halve the length, you quarter the area. This is something people often forget or don't understand or don't appreciate, and here it is in action, which is really nice. But also this this grid of 4 triangles is of course the net of a tetrahedron, and that's that relationship, I suppose, between 2D and 3D and playing around with paper really helps to bring those kinds of relationships home, which is a great delight. Now we've got our center that we found by folding, and what we're going to do now is just take each corner of our triangle. I do hope you're managing to keep up with me, and I apologize if I'm going too fast or too slow. We're going to just take each vertex into the center. And hopefully you've managed to do that. You're following me, and I apologize if I'm going too fast. I apologize if I'm going too slow. I'm apologizing if I'm not making too much sense. And what you have here, I suspect it's fairly obvious, it's a regular hexagon, because each of these little triangles that I've folded in is equilateral. It's similar to the original equilateral triangle I started with. So I have a hexagon, a regular hexagon, and one of the questions I always ask my learners in my groups is, what fraction of the original equilateral triangle is this hexagon? And it doesn't usually take very long for learners to explain, well, you've got 6 triangles, 3 of which are overlapping, so I can imagine the equilateral triangle being made up of 9 little triangles. The hexagon is 6 of them, so the hexagon must be 2/3, and they've got a little bit of fractions in action there. Okay. Now, as I mentioned, the tetrahedron won't hold together on its own. However, sorry, I've got another equilateral triangle here, which has got lots of folds on it. I beg your pardon. So we've made our folds like so. If you now, on those outer 3 triangles, take, and if I was working with learners, I'd have got them to make another equilateral triangle, but I'm conscious that we're running out of time, so I just want to try and do this for completeness. So you've literally, what you've done is folded, you've kind of repeated taking the apex down to the bottom just for those outer triangles. And what you'll find is one of them has got pockets either side into which you can put the little triangles. And essentially this is a frustum of a tetrahedron. Yeah, you've chopped the top off and it holds together. Okay. Now, if you make lots of those, you can glue the trapezoidal faces or trapezium faces together and make yourself an approximate icosahedron. And it will have a hole in the middle. Okay, we'll have a hole in the middle. So you can make another one to go inside. So this is always a very popular group activity. So they make their frustum and then they join them together. If we go back to the one where we've got our folds for going into the center to make the hexagon, and the folds obviously down to the base, that will give you all the folds you need to make a hexagram. Okay, a 6-pointed star. Okay, and again, you can talk about fractions, you can talk about the area of overlap. There's lots of things you can do here with the mathematics. Okay, and I would quite often do this with learners to say, oh, you real stars. With all of your folds, whether you're doing geometric origami as we've been doing, or whether you choose to do some traditional models, one of the things you can do is to pull everything apart and look at the angles that are there. You can look for all the different shapes that are there, and it's a great way of developing language and understanding of geometric properties. The very last thing that I want to do before we finish, because I think we're meant to be finishing talking at 5, so that you can we can take any questions you might have, although I notice there aren't any at the moment, so please feel free to send some, is to take a fresh piece of paper and fold it in half, and I'm going to write the fraction in. So there we go, 1/2, and then obviously this shows I've got 2 halves to make a whole, and I'm just going to halve the other half. So that's obviously 1/4 of the whole. Okay. I perhaps should draw in the folds I've made as well, just to make it clear. And then I'm going to do the same again. Okay, so another fold. And that's an 8. Obviously, 8 of those would make a whole, but 2 of them make 1/4, just as 2 quarters make 1/2. So this is really great for equivalence. And then I'm going to repeat again. And I've got my 16th. Okay, and all those relationships that I just talked about. I'm going to repeat again. And this time I'll get a 32nd. Okay. And then I'm going to repeat again. Okay, so down to 64ths now. Repeat again. So I think that'll be 128. Okay. Repeat again. I'm not going to write that one in. but hopefully you get the idea. I can keep going. There's always going to be some little tiny bit that can be halved. And what we've done here is demonstrated that the sum of the geometric progression, 1 over 2 to the power n, must be 1. Because I don't need any more paper to be able to generate that sequence. So I hope what I've managed to do during my talk today is to just give you some idea of the rich areas of mathematics that are available to you with a piece of paper. There's a whole wealth of things you could do, some of which are in here, but there's also masses of publications. There's many articles in mathematics teaching, maths in school, on Enrich, on using origami in the mathematics classroom. So I really, really hope that you'll want to have a go. And I hope you're going to ask some questions so that we can keep Rachel busy. Okay, so thank you very much for your kind attention, and very good luck in your course.
Thank you, Sue. That was fascinating. I just say I really like the proof that the sum of angles in a triangle is 180 degrees. I thought that was a really nice way of doing it, because I was one of those people that used to tear up the triangles and put them together, so it's nice to see it with paper folding. I've got a question, as nobody else is jumping in there. As a teacher, it can be quite scary to try new things in the classroom, and I'm just wondering, how did it go the first time you used origami in the classroom? Did it go smoothly like it did tonight?
I have to admit that I had everything pre-folded. One of the things that's great when you're in a classroom, with 30 people is, if it's you and 30, there's 31 teachers and learners in the classroom. So the great thing is that some people will be much quicker than others, and they will get things much more quickly than others. So it's really nice to be able to, oh, you've got it, go and help. And I know a friend of mine, and you may have come across him if you've read much from ATM, Mike Collerton. He used to have a little group of people that he would, who were willing to come along at lunchtime and learn things, and then he'd plant them in the classroom, strategically to help. So I think there's various ways you can do it. One of the strategies that someone called Ben Bowring particularly talks about is, rather than trying to demonstrate for yourself, is to have a number of ready-made models. So this is a cube. This is due to Paul Jackson, it's known as the Columbus cube. So you make your models in advance, and then you put them out on the table. And so learners work in groups to figure out for themselves how to make things. So rather than you standing up telling them what to do, they've got to, they pull one apart and then have the other one as a guide, and then they reconstruct. And sometimes they need a little bit of advice on how best to do it, but that's something I use a lot for the cube. And also for this skeletal octahedron, which is, they're both obviously made from 6 parts. And the thing that I particularly like about doing these is that the cubes fit inside the octahedron really nicely. Clearly you need 8 of them, but again, this is demonstrating the property of similarity. Yeah, you've halved the lengths, you quadruple the area, but it's actually an 8-fold increase in volume, which often learners find really difficult. So sorry, that was a bit of a long answer. So that there are quite a range of strategies that you can use, and there are some excellent videos as well as instructions. So there's all sorts of different ways that you can do things. But encouraging learners to figure things out for themselves. And certainly with this, we did a mind experiment, But I remember once going to a classroom, would you believe, in the Czech Republic, where all the children were given some paper triangles and just asked to, you know, find out what they could about the angle sum. So they were just experimenting with the paper and then discovered that actually they could get them to make this rectangle for themselves, which was wonderful.
We've got a few more questions coming through now, Sue. Floriana's asked, are those methods adequate only for Key Stage 1 and 2, or is it possible to adapt them for older students?
Oh, well, all I've shown you today are for older students. You wouldn't, they're not for Key Stage 1 and 2. You wouldn't be able to prove the proportions of a paper with primary children. You wouldn't, you know, and even with these fractions, I would say, whilst you might think they're primary, in secondary, you'll find many children who can't do fractions, so they'll need that help. So yeah, these strategies go across all age groups, I would say.
That's great. Cullum's asking, is there much skepticism towards using the kinds of activities you've demonstrated today? He says he thought he'd be a little dubious before we started, but he can now genuinely see the benefits of using a tactile approach to showing geometric proofs and relationships.
Yes, but that's the same skepticism that you'll come across where people say you don't need to use practical equipment with older children. You know, using equipment is babyish. Well, actually not. It's an aid to thinking. You know, mathematics happens in the head, but doing things with your hands and talking with others can really help to develop your understanding. So, you know, practical resources are valuable for everybody, I would suggest. And it's really interesting that Leonie Burton did some research on how practicing mathematicians work on mathematics. And the interesting thing that she found was that, you know, these really capable mathematicians work on images in the head. They don't go straight to algebra. You know, algebra is the neat stuff for writing up afterwards. In terms of working on things, you often need bits of paper or, you know, scrappy diagrams. You need to play around. So, yeah. And someone asked about this. Is that right? I think that's what you've asked, is it Gabrielle? So you've folded your triangle, yeah, and then you repeat for the outer triangles, and you then look, and one of the triangles will have holes on either side. Okay, in origami they're called pockets. Okay, and then you just pop the triangles inside the pockets. Only one triangle will have pockets on either side. Okay, and then it will hold together. And I apologise because it's got other folds in it. Abby, it is a myth that you need to teach things before you do any practicals with them. My advice is start with something that's intriguing. That makes the learning worthwhile. Yeah. So don't be seduced into thinking I've got to train them into in basic techniques before they can ever solve a problem. It's hotly contested, but you don't learn to do problem solving after you've learnt stuff. Problem solving is actually a way of being and thinking. So you're much better to give really interesting tasks to young people to engage them, and the learning will be better that way. Okay. I think anonymous attendee, I think it's a really good question, but it's about the discussion. It's about the language that they're using. So what does it mean? You know, 100 years ago when I was a teacher, I used to take my classes out onto the field, and we used to do all our locus work, you know, be a certain distance from these people, be a certain distance, you know, make sure you're the same distance from these two markers, you know, make sure you're twice as far from that marker as you are from the other. And we used to have a lesson or so doing this, and it was great fun. But they then spent 2 weeks afterwards constructing it all and making sense of it all in their exercise books. And I think that's, so it's the conversations that you have, and it's drawing attention to what's going on. So, you know, when you fold the hexagon, so what fraction is this? Why? What's going on here? You know, when you've made a fold, pulling it apart and saying, so what are the angles and why? And you know, noticing the properties. So it's I'd call it milking it for the mathematics, if that makes sense. You know, so yes, it was a fun experience. What's the mathematical learning that we can take from that? And obviously, as a teacher, part of it is making those connections to help learners see that that fun task wasn't just a fun task. It actually is, it generalizes, and that's the power of mathematics. Well, Chloe, it really depends what your lesson's about. You know, at the end of the day, you need to be clear what you're trying to achieve in your lesson, and then how the activity fits. But you know, there is a lot of mathematics just in the little bit of stuff that we've done. So folding the equilateral triangle, you know, that if you're thinking, I want my learners to be able to prove things using argument, well, actually proving that you've got an equilateral triangle, proving that you have indeed trisected that angle. There's lots of different ways of doing it, and depending on your learners, so that might be the purpose of your lesson. You know, if you're doing this could be with a group of A-level students, you know, early on in their work on geometric progressions, and helping them to understand how come there are limits to infinity. You know, because it's kind of surprising, because if you take something like, you know, the sequence a half, a third, a quarter, well, that doesn't actually converge. And yet, you know, you take a half, a quarter, an eighth, a 60, that does. Well, you know, wow. You know, there's so many like amazing things in mathematics, and giving learners those experiences that allow them to experience that wowness for themselves is so, I would say, so essential. So again, a long time ago when I was working with beginning teachers, one of my things was, you know, what are you going to get the learners to think about today? John Mason says that a lesson without the opportunity to generalize is not a lesson about mathematics. And I would say that any lesson on mathematics needs to give learners an opportunity to think for themselves, to make connections, to, you know, to start to put together some cognitive rebuilding, if you like, that happens in lessons. So I hope that helps.
No, I think that's great, Sue. Thank you. And can I just say, I think we'll draw it to a close now, but can I just say a huge thank you to you, Sue, for a very inspiring talk, and particularly for doing what should be a practical hands-on session, for doing it so well remotely. I've learned something new today, and I'm sure everybody has. So thank you so much, Sue. Our branch's next talk is on Friday, the 9th of October at 4 p.m. Stephen Lynch will be giving a talk on Python for A-level mathematics and beyond. So that will be of interest to anybody in maths education. So I do hope you'll be able to join us for that. But can I thank you all for joining us today? And I think Sue's happy to hang around for a few minutes after the talk if you've got any questions that haven't been answered yet. But thank you.